Let's review energy changes in nuclear processes. According to Einstein's equivalence of mass and energy, E equals mc squared, an energy change is a mass change in both nuclear and chemical processes. The mass defect between the bonded nucleons in a nucleus, less mass, compared to those same nucleons massed independently, more mass, can be converted into the binding energy per nucleon, which measures the stability of that nucleus. So let's calculate the binding energy per nucleon of nitrogen-14, which has a nuclear mass of 13.999234 AMUs. The fact that we're given the nuclear mass, that is the mass of the nucleons when they're in the nucleus, when they're bonded together. In other words, in the mnemonic that I use, when the nucleons are separate, they're heavier, and when they're tighter, lighter, that 13.9 whatever number is the tighter, lighter number. So I think what we need to do is we need to determine the separate, heavier number. So let's do that. In nitrogen-14 we have 7 protons, and the mass of each proton, you could look this up, or it's in an earlier lesson, is 1.00728 AMUs. Nitrogen-14 has 7 protons. It also happens to have 7 neutrons. Obviously the number of protons and neutrons isn't always going to be equal. It just happens that in the case of nitrogen-14 we have 7 of both. A neutron is slightly more massive, but not much, than a proton, and so the separate, heavier number is right there, 14.11158. So what we want to do is we want to calculate the mass defect, which is the difference between the separate, heavier number and the tighter, lighter. And that turns out to be that. That mass is missing from the nucleus. And what's happened is that mass has been converted into energy. That is, it's been converted into binding energy. What we want to do is we want to take that mass, convert it into an amount of binding energy using Einstein's equation, and then divide by 14, because we're asked to find the binding energy per nucleon. In other words, the binding energy divided by the total number of nucleons. Let's convert the mass defect into kilograms, because in order to use E equals mc squared, we need to have the mass in kilograms. My students are required to know that 6.02 times 10 to the 23rd AMUs is 1 gram, and so to convert AMUs into kilograms, we could show these conversions, and there you have the mass defect in kilograms. Now we're going to use Einstein's equation, E equals mc squared, where we have our mass now. We know what the speed of light is, 3 times 10 to the 8th. We need to square that speed of light, and then we're going to divide by the number of nucleons, which is 14. What we have on the screen now at this point is the binding energy, which is the numerator, per 14 nucleons. And when you do that, you get a number that's this, 1.20 times 10 to the negative 12th joules per nucleon. Just as additional information, we said in an earlier lesson that iron 56 has the largest value of binding energy per nucleon, and you can see that it is, in fact, larger than what we got for nitrogen-14. It's 1.41 times 10 to the negative 12th joules per nucleon. Sometimes binding energy is reported in electron volts, or mega electron volts, or MeVs, or giga electron volts in the case of atom smashers and that sort of thing.